Good afternoon, ladies and gentlemen. My name is Greg Odenthal. I'm the Director of Engineering at ITC, International Technical Ceramics, and I want to thank you for attending this afternoon's presentation on efficiency gains and reductions in furnace maintenance through the use of high-temperature ceramic coatings. I've been involved in the iron and steel industry for 35 plus years. I've held positions at U.S. Steel, SMS Concast and Engineering, one of the world's largest mill builders for continuous casters and rolling mills, as well as Vesuvius USA, a worldwide supplier of refractories. So let's explore the world of ceramic coatings and how they can help you. High temperature, energy efficient ceramic coatings, no longer a theoretical technology, are being used successfully today in furnace applications to reduce energy consumption, improve the temperature uniformities, reduce the high costs of refractory maintenance, and increase production, all while improving product quality. One of the main functions of the ceramic coatings is to increase the emissivity, a material's ability to absorb and re-radiate energy, of a refractory lining in a furnace. These coatings can provide energy savings between 7 to upwards of 25%, depending upon the fuel being used, the furnace operation, furnace configuration, and production schedule. Furthermore, the heat-up time of these furnaces is decreased, and the service life of the ceramically coated refractory is extended. As shown in the graph below, emissivity versus temperature, you can see the values for typical furnace refractories and typical ceramic fiber versus the ceramic coatings. The Sankey diagram shows us the energy losses that occur in a furnace. Knowing the total energy input, we can calculate the amount of energy available to the product, minus any losses due to door openings, wall losses, stored energy in the refractory, other energy losses due to flue gas or heat recovery systems. By completely coating the hot face of the furnace's refractory lining, we can now reduce the opening losses due to the doors, the losses due to the wall, which is the transfer of energy through the refractory lining, and that of the energy stored within the refractory. By reducing these losses, we now have additional energy available to the product. The diagram on this slide shows a comparison of an uncoated versus a coated hot face lining in a furnace. This surface receives the radiant energy output by the burners and transmits it back to the coater body or the product that we are trying to heat treat or forge in the furnace. The efficiency with which it achieves this is related to the emissivity of the surface and the quantity of heat absorbed and re-emitted. As you can see, by coating the hot face lining with a ceramic coating, we can greatly reduce the heat loss through the wall. Ceramic coating technology is based on radiative heat transfer, shown in the equation on this slide. The coating's emissivity, also being a function of temperature, shows that the performance actually increases in hotter temperatures. So, the hotter the environment, the better the coatings perform. The coatings were designed to be compatible with all types of refractory, as well as all ferrous and non-ferrous metals. A unique property of these coatings is that they will move with the dimensional change of the substrate, thus preventing shearing between the coating or the substrate. In order to do this, the binder in the coatings was formulated to optimize the bond strength between the coating and the particular substrate. And once again, for the coatings to be effective, the temperature of the coated surface must be hotter than the load or its surroundings. Let's take a look at some of the benefits of ceramic coatings and their effects on production. These coatings can be used for all refractory and all metal substrates. They can be applied to a hot or a cold substrate. They are electrically non-conductive, so the welding of metallic anchors or the repair of a steel shell of a furnace must be done prior to any application of a coating. There are major reductions in fuel consumption, averaging 10 to 25%. Refractory longevity can be increased by 2 to 3 times its uncoated life, thus reducing the high costs of refractory maintenance. On average, NOx is reduced by 5 to 7%. Temperature uniformities are greatly improved. With the coatings being applied to the entire hot face lining of a furnace, there is prevention of heat loss in all directions. With this prevention of heat loss in all directions comes improvement of product quality through the reduction of cold spots. With the increased amount of heat available, there can be an increase in productivity, as we will see later on in this presentation. The coatings will increase the life of stainless and steel parts due to oxidation at high temperatures. And based on their price, they are an economical means of production of equipment and refractory linings. Application methods and surface preparation are extremely important in the installation of ceramic coatings. Recommended methods of applying ceramic coatings are by spray application using one of the commercially available sprayers shown here. If the square foot area to be coated is relatively small, a typical paintbrush can be used to apply the coatings. Surface preparation by far is the most important step in any coating application. All metal substrates must be clean and free of any dust, grease, oils from machining, oxidation, rust, or paint. Sandblasted is the preferred method of cleaning, and it is recommended that a commercial or near white blast be performed to prepare the surface. The chart on this slide gives a visual description of the substrate requirement prior to any application of a ceramic coating. As for any refractory substrate, all hard cast refractories, rammed plastic, and brick must be clean and free of dust, slag, scale, any carbon buildup, or spalled refractory. If the refractory is in need of repair, it is recommended that it be replaced and dried out per the manufacturer's dry out schedule before any coating installation takes place. All ceramic fiber refractory must also be clean and free of any dust and devitrification. Devitrified fiber is the brown, crusty layer that develops on the surface of ceramic fiber due to high temperature. This devitrified layer can be removed with the use of a currycomb, thus exposing the soft, friable refractory underneath. At this point, it is important to note coating failures and their cause. The number one coating failure is failure to bond. Two conditions typically cause this type of failure: surface contamination, or poor surface preparation, and lack of mechanical bonding area. As previously mentioned, surface preparation is the most important step in any coating application. The slightest oil residue or dust will prevent these water-based materials from adhering properly. Additionally, a lack of mechanical bonding area is usually only a problem on surfaces that are very smooth, ground, or polish. This is another reason for roughing up the surface prior to application, or surface preparation. The second type of coating failure is the failure of the underlying metal or refractory. In this second case, it is the failure of the underlying substrate. If the metal substrate was previously fired, it may have a deep oxidized scale layer. This scale layer will eventually mechanically fail to adhere to the metal layer beneath it and will spall off, taking the coating along with it. The same situation applies to loose or spalled refractory. Again, a good mechanical cleaning is necessary to remove weak material. In this situation, unfortunately, it is often difficult to distinguish what is really happening because failure to bond and failure of the underlying metal surface or refractory surface looks much the same without the aid of a microscope to examine the failure site or a flake of the spalled material. The third coating failure, which is failure of the coating layer, is important as well. This third case is a failure within the coating layer, not that the coating fails itself, but because too thick of an application was applied. Here, shear stresses take over and cause delamination within the ceramic layer and flaking of the coating. It is important to get a thin, even coating applied. Forcefully rubbing the coating material with a cloth, clean brush, or painting pad, if a sprayer is not available, will help to promote good adhesion and evenly coat the surface. Always be careful of buildup in areas where surfaces meet, such as welded joints and corners. The next and obvious coating failure is mechanical damage. If mechanical damage does occur, the recommended means of repair is to remove the loose and damaged ceramic coating layer and reapply the coatings. The last coating failure is extreme thermal shock. Extreme thermal shock, usually associated with winter or cold weather installations where the coatings drop below 40 degrees, are susceptible to a coating failure itself. Care must be taken to fire and cure the coatings before use in a furnace. Curing can be done using torpedo heaters or rosebud torches. In this slide, the photo shows the third coating failure or failure of coating layer. Here we can clearly see the shearing cracks developing due to the coatings being applied too thick. Once again, in this slide, the photo shows the third refractory failure or failure of the coating layer due to too thick of an application on a refractory substrate. Let us now take a look at the efficiency gains and the maintenance reductions achieved when the coatings are properly installed. At North Carolina State University's ceramic department, their clay studio utilizes a Cone 10 gas reduction car kiln. The refractory construction consists of 2600 degree IFB with a sprung arch and 50 cubic feet of area. Utilizing the coatings at a thickness of approximately 3/16 of an inch on the hot face of the IFB, the outside surface temperature of the Cone 10 gas reduction kiln was reduced by 30 plus degrees. The firing time of the kiln was reduced by 1 hour and ramp up to Cone 10 reduced by 20 minutes. The clay studio at NC State University also utilizes a barrel raku kiln with 2.5 inches of ceramic fiber lining. This time, approximately 1/8 of an inch of ceramic coating was applied, and the outside surface temperature was reduced by 50 plus degrees. The firing time of the kiln was reduced by half. The gas consumption reduced by greater than 1/3. And since August of 2017, NC State has done zero maintenance to the ceramic fiber since the coating installation. At McConway Twirly in Pittsburgh, Pennsylvania, they utilize an austenizing furnace with a 12-inch ceramic fiber folded module construction. A ceramic coating was applied at approximately 1/8 of an inch thick to the hot face of the fiber lining. After coatings were installed, the temperature uniformity improved from plus or minus 40 to plus or minus 25 degrees Fahrenheit, or a 45% improvement. Fuel consumption per load was reduced from 20.8 MCF down to 18.7 MCF, or a 10% reduction. Turnaround time reduced on average by 20 minutes. Due to the reduction in turnaround time, a production increase was realized by 1 additional load per week. At W. Abrasives in Ontario, Canada, a blasting media manufacturer, they utilize a retort furnace with an IFB, or insulating fire brick lining. Ceramic coatings were installed at approximately 3/16 of an inch to the hot face of the IFB lining. After the installation of the coatings, a reduction in fuel consumption by 7% was realized. Additionally, refractory longevity was extended by 3 times the normal uncoated life, thus greatly reducing their high costs of refractory maintenance. On a much larger scale is the reheat furnace at ArcelorMittal's Harriman, Tennessee plant. This furnace operated at 2,350 degrees Fahrenheit with a designed throughput of 75 tons per hour and an efficiency of 1.2 million BTUs per ton of steel produced. The coating installation for this furnace used a veneering process. The veneering process is a 3-part or 3-day installation consisting of Day 1, coating the entire hot face refractory lining. Day 2, saturating pre-cut 1/2 inch thick, 12-inch by 12-inch square, 2600 degree ceramic fiber blanket and adhering it to the coated hot face. Ceramic coating sticks very well to ceramic coating. Day 3, spray coat all installed ceramic fiber squares. This process is usually required on an aged, hard-cast refractory lining with spalled, cracked refractory due to thermal shock, heat load, and age. Because the coating is only applied in a thin layer, there is no way to seal and fill the cracks in the lining. All avenues for excessive heat loss to travel to the shell. The saturated ceramic fiber blanket is used to bridge these gaps and cracks, thus sealing the furnace and preventing heat loss. With the installation of the veneering process complete and the furnace back in operation, let's review the benefits of the newly coated furnace. Operating 3 days per week and producing approximately 156,000 tons per year, the fuel consumption was reduced from 1.2 million BTUs per ton down to 0.8 million BTUs per ton of steel produced, or roughly a 33% reduction in fuel consumption. At a cost of $8 per million BTU, their yearly fuel cost was reduced from $1.5 million to $1 million per year for an annual savings of $500,000. ArcelorMittal reported an approximate reduction in scale of 2.5%. A reduction in scale led directly to an increase in yield of an additional 3,900 tons. At a cost of $450 per ton, this equated to an increase in profits of $1.7 million. In addition, the furnace startup time, after an outage, was reduced by 5 hours. With all of these benefits and process improvements combined, the ROI for this coating installation was 1.3 weeks, or approximately 10 days. In conclusion, the potential application of high-temperature, energy-efficient ceramic coatings cuts across a wide spectrum of thermal process industries and types of equipment. Numerous installations, in addition to those that were discussed here today, have proven successful in forge and heat treat furnaces, reheat furnaces for steel manufacturing, tunnel kilns and brick plants, refinery and petrochemical process heaters, cement kilns, and utility boilers. In the same manner, coated metal substrates are protected from high temperature oxidation, corrosion, and thermally induced stresses, thus extending the life of these metal parts for years to come. Thank you, ladies and gentlemen, for attending today's tech session presentation on efficiency gains and maintenance reductions through the use of ceramic coatings. If I can answer any questions or be of service to you, please feel free to contact me either via email or my cell.